Welcome back, everyone, to our ongoing deep dive into the OEIS, the Online Encyclopedia of Integer Sequences.
Yes.
Today we're going a little further down the rabbit hole, I guess you could say, into deeper, to this treasure trove of numerical patterns.
Right.
And today's sequence, I think, is going to be particularly interesting for number theory students out there.
Absolutely.
000111,
Yeah.
also known as the Euler or up-down numbers.
It's a great one to pick because it's just such a beautiful example of how, like, really simple combinatoric ideas encode, like, deep mathematical truths and also bridge, like, seemingly disparate fields like we're going to be talking about, like trigonometry, calculus today.
I'm ready.
Pretty cool stuff.
So for our listeners who might not have encountered this sequence before, let's start with the basics. What exactly are these Euler up-down numbers?
Sure. So at their heart, they're all about counting alternating permutations.
Okay.
So, imagine you have a set of numbers, say like 1 through 5. An up-down permutation is an arrangement where the numbers alternately rise and descend.
Okay.
So, for example, 1, 3, 2, 5, 4 would be an up-down permutation.
Okay.
Because 1 is less than 3, 3 is greater than 2, 5 is greater than 4, and so on.
Okay, so it's like a numerical zigzag pattern.
Exactly.
Yeah.
And then, of course, we also have down-up permutations where the pattern is reversed.
Right.
So now the nth term in our sequence, A000111, counts both the up-down and down-up permutations for a given length.
Okay.
And it's interesting to note that, like, for length 0 and 1, there's only one unique permutation.
Right.
And we consider that to be alternating just by convention.
Okay. I'm following you so far with the alternating permutation idea, but how do we actually count them?
Right.
I imagine it gets pretty complicated as n gets bigger and bigger.
Yeah, absolutely.
Yeah.
So that's where what's known as Andre's problem comes in.
Okay.
So a 19th century mathematician, Desire Andre, tackled this very question of, how do we determine the number of alternating permutations for a given n?
Right.
And his solution is quite remarkable because it involves trigonometry.
Trigonometry. Now, that seems to be coming out of left field a little bit.
Yeah.
How did he even connect those dots?
I know, it's a bit strange. So what he did was he discovered a recurrence relation for the sequence.
Okay.
Meaning he found a way to express a term in the sequence based on the previous terms. And it turns out that this recurrence relation can be translated into a differential equation.
Wow.
Which, when solved, leads to this very elegant trigonometric formula.
So you're saying that this connection to trigonometry, this is just the tip of the iceberg?
Yeah, just a hint of the connections.
What other surprising relationships does this sequence have?
Buckle up, because A000111 also has ties to Bernoulli numbers.
Oh, wow.
Another important sequence in number theory.
Yeah.
And there's actually a formula that relates the two sequences.
Okay.
And it uses factorials powers of 2, and of course both the Euler up-down numbers and Bernoulli numbers themselves. It's a little bit too complex to state here, but it just shows how deeply intertwined combinatorics and number theory really are.
Wow, this just keeps getting more and more interconnected. I'm starting to see why this sequence is so fascinating. It's like a mathematical spider web, linking all these different concepts together.
It really is, and there's more.
Okay.
So remember I mentioned trees earlier?
Right.
Well, it turns out 000111 also counts something called increasing 0, 1, 2 trees.
Okay, now those sound interesting. What exactly are increasing 0, 1, 2 trees?
So imagine you're building a tree-like structure, but each branch point or node can have one of 3 labels, 0, 1, or 2.
Okay.
And the rule is that as you move down any branch, the numbers on the nodes must always increase.
Okay.
So like you're climbing a numerical ladder, always going up.
Okay.
And the number of these trees with n nodes is also given by the nth term in A000111.
That's pretty wild.
Yeah.
So we've got permutations, we've got trees, we've got trigonometry, we've got Bernoulli numbers.
Yeah.
What else is this sequence connected to?
Well, there are also ties to something called integer numbers,
Okay.
which count certain types of permutations.
Okay.
And then to add like another layer of connection, the even index terms in A000101 are called second numbers, while the odd index terms are called tangent numbers.
Wait a second. Second and tangent numbers. Didn't we just see those with Andre's theorem?
Right.
And the trigonometric connection.
Exactly.
Okay.
So this terminology ties back beautifully to that generating function we discussed earlier.
Right.
It just further emphasizes how deeply interconnected these concepts are.
Yeah.
We're seeing how a sequence that starts with simply arranging numbers leads us to all these fascinating mathematical relationships.
It's mind-blowing how much depth there is to this seemingly simple sequence.
Yeah.
For our number theory students, this must be like finding hidden treasure.
Absolutely. A000111 is a prime example of how seemingly different areas of mathematics can be intertwined in surprising and elegant ways. And we've only just scratched the surface.
I'm eager to dive a little bit deeper, but before we do that, let's make sure we have a solid understanding of the formula itself. How do we actually calculate these Euler up-down numbers?
Right, so let's take a look at the explicit formula for A000111.
Okay.
It's a bit more involved, but it lays bare the mathematical machinery behind the sequence.
Okay.
And it involves something you might be familiar with from your number theory studies. Stirling numbers.
Okay, I'm ready to see this formula and all of its complexity.
All right, let's do it. All right, so Stirling numbers of the second kind, often denoted as SNK, they basically count the number of ways that you can partition a set of n objects into k non-empty subsets.
Right, okay.
So for example, imagine you have like 5 different colored balls and 3 identical boxes.
Okay.
The Stirling number of the second kind would tell us how many ways we can distribute those balls into the boxes, ensuring that no box is left empty.
Gotcha. Okay, that makes sense. So how do these Stirling numbers play into the formula for our Euler up-down numbers?
Well, the explicit formula for n, which is the nth up-down number, is a sum over k from 1 to n.
Okay.
Each term in this sum involves a Stirling number of the second kind, Sn, k, multiplied by a couple other factors, so k factorial, 2 raised to the power of 1 minus k, and a binomial coefficient.
I'm seeing factorials, powers of 2 binomial coefficients, all the classic combinatorial tools.
Exactly, and that really highlights how deeply intertwined combinatorics and number theory are.
Yeah.
This formula, with all its combinatorial elements, really cleverly gives us a way to directly calculate any term in our A000111 sequence.
So this formula gives us a precise way to calculate any term in A000111. But what if we want to understand how the sequence behaves as n gets really large?
Right.
Like how quickly do these Euler up-down numbers grow?
That's a great question, and that's where the concept of asymptotics comes in.
Okay.
Asymptotics give us an approximation for n when n is very large.
Okay.
And this is where things get even more interesting with A000111 because its asymptotic formula involves pi.
Hold on, pi. The ratio of a circle's circumference to its diameter is showing up in a sequence derived from permutations.
Yeah.
How is that even possible?
I know, it's pretty remarkable, right?
Yeah.
So the asymptotic formula tells us that as n grows, n is approximately equal to 2 times 2pi raised to the power of n plus 1, all multiplied by n factorial.
Yeah.
So even though A000111 starts with this very simple concept of counting permutations, its long-term behavior is governed by pi.
That's an incredible connection.
It is.
What does this unexpected appearance of pi tell us about the nature of this sequence?
Well, I think it speaks to the profound interconnectedness of mathematics, right?
Yeah.
The fact that pi, a constant that comes from geometry, emerges in the long-term behavior of this sequence that's rooted in permutations. Suggests that there are deeper, perhaps yet undiscovered relationships that link these seemingly disparate fields.
Yeah.
It's really a testament to the power and elegance of mathematical tools and kind of encourages us to keep exploring and looking for those deeper connections.
It's like these seemingly simple combinatorial ideas are encoding like profound mathematical truths that bridge all these different fields of math.
Absolutely.
This is really making me rethink like my understanding of how all these different areas relate to each other.
Yeah, and that's the beauty of sequences like A000111.
Yeah.
You know, they can open up entirely new ways of thinking about mathematical concepts and their connections.
Totally.
We started with the simple idea of alternating permutations, and now we're talking about trigonometry, Bernoulli numbers, trees, and even pi.
I have to admit, I'm completely captivated by A000111 now. I feel like we've only just scratched the surface of its secrets.
Yeah, there's so much more to explore.
But before we wrap up our deep dive today, I want to make sure that we've given our listeners a good overview of everything that we've covered.
Absolutely.
Okay, so we've journeyed through this intricate world of A000111, the Euler, or up-down numbers.
We have.
We started with this simple idea of alternating permutations and uncovered this web of connections to other mathematical concepts.
I know, it's amazing how much is packed in there.
So we saw how Andre's theorem links these permutations to trig functions. And revealed this surprising connection to second and tangent numbers.
Yeah.
And then we explored how A000111 relates to other important sequences, like Bernoulli numbers and integer numbers.
Yeah, and even trees.
And even to that fascinating world of increasing 0, 1, 2 trees.
Yeah.
And of course, we can't forget that mind-blowing appearance of pi
Right.
in the asymptotic formula for A000111.
Yeah, it just kind of comes out of nowhere.
It really does highlight that interconnectedness of math,
It does.
with, a constant from geometry governing the long-term behavior of a sequence that's rooted in combinatorics.
Right, and I think A001111 is like such a good example for number theory students.
Yeah.
Because it shows how like exploring seemingly simple combinatorial ideas can lead to these really deep and unexpected connections across different fields of mathematics. It really encourages us to look for those hidden relationships and to just appreciate the elegance and unity of these mathematical concepts.
Well, as we wrap up our deep dive today into A000111, I'm left with a sense of wonder
Yeah, me too.
and a desire to explore further.
Absolutely.
I have one final thought-provoking question for our listeners,
Okay.
especially for those budding number theorists out there. What other secrets does A000111 hold? Can you delve even deeper into its connections within number theory
Right.
and uncover even more fascinating relationships or patterns? The OEIS is this vast and wonderful playground for mathematical discovery, and A000111 is just one of many captivating sequences waiting to be explored.
It really is. Every sequence in the OEIS has a story to tell.
Yeah.
And every exploration, every connection we uncover just enriches our understanding of the mathematical world.
Totally.
So keep exploring, keep questioning, and keep seeking those beautiful mathematical connections.
Thank you for joining us on this deep dive into the fascinating world of A000111. We'll be back soon with another intriguing sequence from the OEIS, so stay tuned.